So here's Will Roper, and he will tell us about the flares simulation. Here you go.
Right, yeah. So,
yeah, can you? There we go.
Oh yeah, sorry. Hi, I'm Will Roper. I'm a second-year PhD student at the University of Sussex, and yeah, I'm going to talk about the sizes of galaxies at high redshift in flares, which builds on the work of some of my collaborators shown here. Chris, who will be talking exactly after this talk, and Ashwin, who will be talking later. So I'm going to start by giving just a quick primer on flares. I will try to make this quick, as you will hear this 3 times today, but flares is a suite of 40 zoom simulations. They're these 30 megaparsec spheres you can see rotating here. They're simulated with full hydrodynamics using the Eagle model and are pulled from a 3.2 gigaparsec parent box and simulated down to a redshift of about 5. And what this approach allows us to do is cover a really large range of overdensities from the extremely overdense extreme regions, which we focus on in Flares 1, which are up in the top left of this little animation, right down to the really, really underdense regions, which are down in the bottom right. So anyway, with that primer out of the way, on to sizes. So when we initially looked at the half mass radii at these high redshifts, we were somewhat surprised by what we saw. So what you find are these distinct populations. So firstly, there's this high mass ultra compact population, which will be the population I'm going to focus on in this talk. And then there's also this low mass diffuse population, which is a whole another topic in itself that I'm going to skirt around in this talk, but more than happy to talk about on Slack or just in discussions. And then you also have this third unimportant population, which is, I leave it in at this point purely to highlight that you should never trust your Halo Finder 100%. These are spurious galaxies that have basically been torn out of a parent galaxy just because there was a density saddle point. And in all future plots, they're recombined into the galaxy they were orphaned from. And another just sort of point of worry when we first saw these, so this high mass population are all below the half mass radii are all below the softening scale of the simulation. So yeah, initially worrying when we first looked at it. And just to quickly say, so this is the half mass radii relation, but across a selection of snapshots we have. So this dual population sort of evolution starts at redshift 12. It then continues throughout the time of the simulation. So right down to our final snapshot, 4.77. So the question stands, is there an issue in the subgrid model at high redshift, or is this actually a reflection of reality? And the only way we can find that out is if we compare to observations. So to that end, we create synthetic observations using synthobs, which you heard a bit about on Monday from Madeline. This was written by Stephen Wilkins, one of my supervisors. We take a bunch of stellar properties, input them to synthobs. That gives us fluxes for those stellar particles. And then we propagate the luminosities or fluxes of these stellar particles along the line of sight using code written by Ashwin to get dust extincted fluxes or luminosities. We can then take those fluxes and smooth them over some kernel, be that Gaussian, cubic, or quartic, or quintic, to create images that represent the underlying stellar population that the stellar particle represents. So, and from these images, we can then measure half-light radii. So this is the size of the luminosity relation at redshift 5, but for the intrinsic luminosity. And unsurprisingly, this just traces the underlying stellar distribution. So you again have this sort of 2 populations of one bright, high mass compact, and one diffuse, low mass and low brightness population. But things begin to get interesting when you actually include dust. So this plot is again the size of the luminosity relation, but now we're focusing on the massive, the high mass population. The black points are the intrinsic from the plot before, and then the coloured points are the observations with the dust included. And what you see is this increase in size when you're taking dust into account. So that's beginning to look a bit more promising now. We're not looking at these really, really compact galaxies. They're starting to puff up a bit, but the question is why? Why is this happening? And you might be able to guess, sort of, just by looking at and knowing your physics, that it's the concentration of dust. So these exceedingly compact cores are producing metals fairly rapidly and seeding the core with dust, which then extincts the flux, and you actually see the outer edges much brighter than the inner parts, leading to a much higher perceived size when you're looking at the attenuated fluxes. But that's promising, but not actually comparing to observations. So now we compare in this plot simply to a Kawamata paper from 2018, and we see plausible agreement. So at these redshifts, the observations are fairly sparse, but really, really encouragingly, when we saw this, there is a good agreement between the fits from Kawamata and our distribution from the high mass compact population. The sort of caveat to this is flares focuses on these really extreme regions, and hence you get this large scatter at high luminosities, which isn't necessarily present in the sample. But sort of the obligatory point here being that, as we've heard this week, Webb will give us a wealth of data, and we'll be able to hopefully populate.
Sorry, can we hold on for a second?
Yeah.
I'm not seeing the slide for some reason.
Ooh, really?
Oh,
I see it okay.
Okay.
Maybe it's just me.
Don't know, it might just be lag.
Yeah, I think the rest of us are okay.
Okay. Sorry, in the interest of time, I'm gonna continue.
Sorry.
Yeah, no. So yeah, essentially we have a plausible agreement with observations, and I'm looking forward to getting a wealth of data at these redshifts to actually sort of nail it down a bit better. But I've sort of promised that I'm going to talk about evolution in my abstract. So with the time I've got left, I'm going to just quickly say, on the left here is the flares plot that I showed before of the half mass radii, the stellar half mass radii, and then on the right, I continue to trace that down through the Eagle reference box, down to low redshift, and you can see at around a redshift of 3, so this panel here, the compact population begins to increase in size. So how is that happening? Why is that happening? And there's a few pieces to that puzzle, or 2 main ingredients, in fact. And the first is extended gas distribution. So these are just plots of the stellar half mass radii versus the gas half mass radii. And you can see that almost all of these stellar distributions are associated to an extended gas distribution. And it's just not star forming. And if you actually take a look at the compact gas populations, you see that they're all satellites. So there could be some halo finder effects in there. It's hard to say without diving in. The other ingredient that goes into this is actually the subgrid model itself. So in the Eagle model, star formations and stellar feedback are governed by the gas density at the point of star formation and the metallicity. And if you look at the evolution of those through to low redshift from flares into the Eagle boxes, you find a decrease in the density of star formation and an increase in the metallicity. So as the metallicity increases, it becomes easier to form stars in lower density. So this begins to, combined with the extended gas distributions, you get this picture of really, really compact cores that are undergoing runaway star formation at high redshift, and then at some point later, around redshift 3, the metals mix just enough into the surrounding gas to begin their own star formation, and you get this puff up of the size of these galaxies. So just quickly to summarize that, we've found in the Eagle model at high redshift, you get these intrinsically ultra compact galaxies beyond stellar masses of 10 to the 9. But then when you actually include the effects of dust, we get a good agreement with the observations. And then obligatory Webb point. And then I've presented this plausible evolution track where you have compact cores surrounded by non-star forming gas that turns on at later epochs. And just to say, I'm going to be hopefully putting multiple papers from this up on archive soon. They're just all still in the works. And finally, and I might eat into questions ever so slightly to do this, but the what's next is quite exciting. So flares 2. We're going to aim for at least 10 times more regions. So instead of 40, we're going to have 400. This will allow us to cover various environments a lot better. And we're also going to run with the Swift hydrodynamic code rather than Gadget and the Eagle XL subgrid model. But possibly the most exciting part of this, and also because it just leads to other science entirely, is that we're going to be pulling from a parent at least 8 times larger, but hopefully 16 times larger than Flares 1. So this is a 12.8 gigaparsec box at the same resolution as the original parent. And what's exciting about that is, to our knowledge, it's the first DMO that's going to cover the entire Hubble volume out to redshift 5 at this resolution. So I'm really looking forward to sort of killing some supercomputers with that. And with that, I will finish. Thank you very much.
Fantastic. Okay. Yeah, impressive stuff. So, yeah, do we have questions?
So Tom is asking, it might be worth comparing the density at which the stars form in the compact galaxies to the density above which Eagle supernovae feedback is known to fail.
So that's yeah, I have actually done that. So this mass regime at which you see the compact cores begin, so 10 to the 9, you can actually move that if you increase the feedback fraction. So there is some direct tie there. It's the old overcooling problem, basically.
Okay. Daniel is saying, nice talk. Which process can create these compact cores with sizes below the softening scale of the simulation?
Sorry, I just think through the question. So it's more that so the way these form is you get these high density points within the gas distributions, and then they basically saturate the probability to create a star particle, and then also saturate the feedback. So the amount of energy that is given into the surrounding gas is maximal, but it's just not enough to have any effect on the density in that region. Which then means that you just keep amalgamating mass in a high density point, and then making it easier to form stars by seeding that gas with metals, and not being able to puff it out into and mix it into the surrounding material. I hope that answers the question somewhat. It's sort of it's all in the subgrid prescription what actually drives this. If I have another, just say on Slack, call me out, and I will try and do a better job.
Yeah, I guess I can jump in if there's another question. So I was just, I mean, it is sort of following up on Danielle's point that it does seem to be fairly sensitive to this particular prescription for star formation and the metallicity dependence of that. Have you compared that to things like, you know, there are some simulations out there with full H2 and stuff, and see if the metallicity dependence and density dependence actually follows the trend that's being assumed in Eagle?
No, I haven't, but it would be very interesting to do. We sort of discussed, sort of as a collaboration, we discussed modeling H2 and doing comparisons there. Just haven't got around to it yet. But yeah, there's some interesting stuff going on with the subgrid prescriptions that I probably can't talk about for future stuff, which sort of does tie into this to a certain degree.
Excellent.